Hey everybody, welcome back to the Related Rates channel. Here we go. This video is going to show you a little bit about volume, doing a related rates problem involving volume. Now this next category, area, volume, surface area, all that stuff, I'm not going to be able to do a problem on every type. So it's really the process. You've already done Pythagorean theorem, you've done some ones involving trig, and now here's going to be one involving volume, the volume of a cone specifically. So here's our situation. If you look down here, it says water is flowing into a cone with a height of 16 centimeters and a radius of 4 centimeters. And it's flowing in at 2 cubic centimeters per minute. So as soon as I see that it's flowing in and I see this cubic centimeters, I should be thinking that that is a volume. That's how the volume is changing. How fast is the water level rising? That means our height. When it is 5, 10, and 15 centimeters deep. And you know we'll only do one of these. We'll pick 5. We'll do 5 and go from there. So let's look at our little animation here first. So there it is filling up. Okay, now what do you notice as this fills up, as it gets higher and higher and higher here? You should kind of notice something. I'm going to show the dH/dt. And if you look at dH/dt, look what's happening. It's getting smaller and smaller and smaller until it's full, because as this radius is getting larger, even though the water is being pumped in there at a constant rate, it's taken, it has to fill a little bit more of the container compared to here. And that's why it's so quick to go up. And this is the situation we're looking at right here when the height is 5. Okay, so we're trying to find out how fast the water level is rising. So let's go over to our active inspire. Here we have. And we have our cone. It had 16 feet. Now I want to tell you something about cones. They have this neat little property. I'm sorry, they're not feet, are they? I think they are centimeters. I want to be consistent. Here's a centimeter. And this down here is also centimeters. So here we are, centimeters, centimeters. The cool thing about cones, a right cone especially, or a right cone, is that, see how this radius is 4 and this is 16 height? So that ratio, it has a ratio of radius to height. So that means when this is, the problem asks us to find when h is 5. So when the height is 5, so we're trying to find it right here when height is 5 centimeters. So that means that this radius would be 1/4 of whatever this height is, because it stays that way all the way down and stays that consistent. That ratio stays consistent throughout the cone. So 4 centimeters to 16, this would be 1/4 then of whatever my height is here at 5 centimeters. Okay? So keep that in mind as you're doing some other volume problems, especially dealing with cones. So we have our dreads that we have to come back. Our diagram, there we go. Our rates. So we're trying to find our rates, or what our rates are given. The rate that's giving is, and we already talked about it, is that dV/dt. It's how the volume is changing. And we know that because it's cubic centimeters per minute. I think it was per minute. Yes. And what are we looking for? We're looking for how this height is changing. So we're looking for dH/dt, and we're looking for it specifically when h is 5 centimeters. Okay? So let me move this little idea over, this little ratio. There you go. And so we're going to need an equation now. So diagram, my rates, what I'm looking for, and what I have. An equation. Well, it's going to be the volume of this cone. And the volume of a cone is pi r squared h. I paused for a second there because that is not the volume. The volume of a cylinder is pi r squared h. The volume of a cone is 1/3 pi r squared h. And I don't know if back in a geometry class your teacher may have showed you that if you fill up a cone and you have a cylinder of the same height and radius, it will take 3 cones full of liquid to fill up the cylinder with the same height and radius. And that's why the volume formula is 1/3. So, okay, we have our equation. Now it's time to take the derivative, but before we take the derivative, let's go through this. Okay, if I take the derivative of a volume, I'm going to get a dV/dt. Is that okay to have a dV/dt? Absolutely, because look, we're given a dV/dt right here. If I take the derivative of an r, I'm going to have a dr/dt. Do I have any dr/dt? No, I don't. So how am I going to get a dr/dt? We'll have to come back to that question. If I take the derivative of an h, I'm going to get a dH/dt. Oh, that's what we're looking for. That's fine. But this r is going to cause a problem because we have no dr/dt and we have no way of finding dr/dt. So maybe we have to come up with some way to eliminate that r. Maybe write an expression in terms of h. So think about that. Well, maybe we can deal with this and deal with this. We said that the radius was 1/4 of the height, or that the height was 4 times whatever the radius is. So can I write something in terms of r? The radius is equal to 1/4 of the height. The radius is 1/4 of the height. And that is true everywhere, whether our height is here or our height is here down at 5. So we can use this. Now this is not true for, this relationship is true for all cones, but not that it's 1/4. If this were 8 and this were 16, it would then be 1/2. So that varies with situation. But this idea of creating this ratio is true for all cones. Right cones. So, okay, let's use that. So we have volume equals 1/3 pi. Now instead of r, we're going to put in there 1/4 h squared times h. Now before I take the derivative, let's simplify this a little bit. Multiply let's do this. We have 1/3, and I'm going to show all the steps. This becomes 1/16 h squared times h. So now I have 1/48 multiplying 3 times 16. H squared times h is h cubed pi. That's a nice little equation. Now remember, pi, we could actually write this like this. Because pi is just a number. Don't forget that. So let's take the derivative now. So the derivative of the volume is going to be dv dt. The derivative of this is going to be, remember, this is just a number, is going to be 3h squared. So 1/48 pi is going to be there, times 3h squared dh dt, because again we're taking the derivative with respect to time. So here's our situation. We can simplify this. Get 1, this becomes 16. So I'm left with dv dt is equal to pi over 16 h squared times dh dt. Now, that's our derivatives. Our last one is substitute and solve. I'm trying to find dh dt. I have my h and I have my dv dt, so it should be quite simple. So let's go to our next page. dv dt is equal to pi over 16 h squared dh dt. Did I miss anything? Let me go back and check. H squared, nope. So let's plug in our 2 for our dv dt, our 5 for our for h. So 2 equals pi over 16 h squared dh dt. This ends up becoming 2 equals 25 pi over 16 times dh dt. We can divide both sides by this big monster number. 25 pi over, it's not really a monster number. It's just a funny looking number. And what do I get? Well, when I do all this, and I'm going to bring it up here, I get my dh dt, how my height is changing, to be 32 over 25 pi. And if you had a calculator, you could figure out what that approximation is. Again, when you divide by fractions, you're multiplying by the reciprocal. That's how I get the 32. And it's centimeters per minute is the units. And units are very important. So there's our dh dt. Now the rest of the question asked you to, where are we? There you go. To find it when it's 10 centimeters and 15 centimeters deep. So, how's my height going to be changing? How's my dh dt going to be changing? Is it going to be smaller than when it was 5? Is it going to be larger than when it was 5? So think about those things when you do these problems. So I'll leave those as an exercise for you, is to practice when h is 10 and h is 15. Everything else would remain the same. So you try. Now again, you could use this video and watch it as many times as you want, or skim through it as fast as you can, however you want to do it, but be prepared that when you're faced with a volume question, now every question is a little different and it varies a little different. This is just one example, and you might see some other videos that deal with area, volume, etc. But here's the one on volume of a cone. I hope you enjoyed this. John Stone, out.